Hello friends, welcome back to the mathematical room. I am the caretaker. So we have already seen the development of the system of natural numbers, right? In our previous videos. Now the next natural thing to do is to move on to the system of integers, which consists of the set of integers along with the two algebraic operations of addition and multiplication, which as we will see are going to be natural extensions of these operations. And also we are going to extend the ordered relation that we have in the system of natural numbers to the system of integers. But before we get to this, we have to look at set theory. Now we have already seen naive set theory. This is something we have already seen in our previous videos. However, when we discussed naive set theory, there we came across a problem known as the Russell's paradox, which shows that the intuitive definition of a set as a well-defined collection of distinct objects is not enough for all the collections to be called sets. I mean, all well-defined collections of distinct objects are not necessarily set, or rather we can put it in a more appropriate way like this. The definition of a set as a well-defined collection of distinct objects is not enough to decide that a given collection will be well-defined or not. Remember, we came across a collection and we were not able to decide whether a particular object belongs to that collection or not. That is essentially the Russell's paradox. So to get rid of those things, we have mentioned there itself when we discussed this thing that some axioms are needed to be put into set theory to restrict it in such a way that such collections do not arise as sets. So that's what we are going to do in axiomatic set theory. And the approach is much like how we developed the system of natural numbers. That is, if we quickly recall what we did here, we introduced 5 axioms. The first one was that 0 is a natural number. The second one was that for every natural number n, there is a successor n plus plus. So using these two initial axioms, we then tried to define natural numbers, but we soon discovered that they are not sufficient. So we were forced to devise more axioms. Eventually we devised 5 axioms and they came to be known as the piano axioms, and then we saw that they are adequate or sufficient for defining the natural numbers. And then we proved all the basic laws about this system. Now here also in axiomatic set theory we are going to take a similar approach. We will start with a set, namely the empty set, and we will impose some restrictions on sets and also some operations in the form of axioms which will help us generate new sets from old given ones, just like how we generated new natural numbers from given natural numbers. We started with a single natural number and we used the incrementation operation to generate more natural numbers. So that's what we are going to do here also. I mean, a similar thing. We start with a single set and then we move on to more and more complicated steps. So the way we will start this, we are going to get rid of this definition of a collection that is well defined to be a set. So we are not going to say what well defined means. We are going to present the axioms one by one and they will decide what collections are going to be called sets. So the beginning of axiomatic set theory we will start with a very loose definition of sets. and then we will present the axioms one by one as we go along. Now here there are some points that need to be mentioned. One thing is that we are going to use a list of an overcomplete list of axioms. Overcomplete in the sense that some axioms will be consequences of other axioms. But why this extra burden? It's not a burden actually, it's done for pedagogical reasons. The thing is that our aim is not studying set theory for the sake of studying set theory. That is, we are not going to study set theory from a logical point of view, where we are supposed to come up with the most economical set of axioms, the fewest possible axioms that capture set theory, the basic ideas of set theory. But we can have many axioms which some of them are consequences of other axioms. They serve the purpose of showing the different aspects of set theory more clearly. Here, however, as opposed to this approach of having an overcomplete list of axioms, when we saw the natural numbers, when we developed them using the piano axioms, there we saw that the 5 axioms that we laid out there, they are necessary. The system of natural numbers, or rather its behavior, cannot be properly pinned down if we remove even one axiom from this list of 5 axioms. So in that sense, all the axioms here are necessary, and none of them is actually a consequence of the other axioms. That is not the case we will have here. Some axioms will be, in fact we will show that some of them are going to be consequences of the other axioms. But having a list of many axioms actually makes us see the many aspects of set theory. So that is one point. Okay, and one more thing is that, so this is the 3rd chapter of Terence-Tau's notes, and in this chapter we are going to look at the more elementary aspects of set theory, axiomatic set theory, and the more advanced things such as infinite sets, the axiom of choice. These things are going to be treated in chapter 8. So we have some time before we get to these things. Also, one more thing is that a study of all the subtleties of set theory, all the finer details of set theory, and the much more advanced topics is well beyond the scope of this text. And it's also not our purpose to study set theory from a logical point of view. This set theory is an entire subject in itself, which lies more in the realm of logic than the realm of mathematics. So we are going to look at those parts of axiomatic set theory that are necessary for mathematics, for our mathematical purposes, simply because of the fact that every branch of mathematics has been written in the language of set theory, and its ingredients like sets, functions, those type of things. Okay, so let us start with the 3rd chapter, and it starts with the first section, which is fundamentals. So this is section 3.1. Fundamentals. Okay. Now, the first definition, as I have already said now, the first definition of sets is a rather loose definition. Definition 3.1.1. It's so loose that it comes with the word informal. By now you already know what informal means in definitions, examples, etc. We have already seen this. So what this says, a set is an unordered collection of objects. Is an unordered collection of objects. For example, three, 4, 5, 9. Okay, so the fact that this is a loose definition can be clearly seen from the definition itself. A set is an unordered collection of objects. We are not saying at all what type of collections we are supposed to take. We are just simply saying a collection of objects. So this is a vague notion of sets rather than a definition. That's why the term informal. Now, for an object X and a set A, we say X lies in A or X belongs to A or in symbols we write like this. These things we already know from naive set theory, but for the purpose of for the sake of completeness and presentation, we are just going to show whatever is available in task notes. Or this, if X is an element of A, for example, say 4 belongs to this set. If X is not an element of A, we write like this. Okay? So if X is not an element of A, then we strike this out. Now, you can see that this definition, although it's intuitive, it's insufficient for many purposes. Actually, it's insufficient for almost everything other than the fact that it just gives you a vague notion of sets. We haven't said at all what type of collections are going to be considered as sets. Also, this definition does not say anything about which sets are equal to some other sets. And the definition says nothing about how we can perform some operations on sets like union, intersection, those things that we have already come across in naive set theory. This definition does not say anything about that. So it just gives us a vague idea of sets. Now we are going to rectify that by introducing the axioms. So what sort of axioms we will introduce, that will decide what type of theory we will ultimately have. And obtaining these axioms and seeing what their consequences, elementary consequences are, that will be the main aim of this section. So let us straight away look at the first axiom. So this is axiom. I think sometimes the ink is coming, sometimes it's not coming. Anyway, so this is axiom 3.1. Let me just first write down the statement and then we will try to understand what it means. Sets are objects. It may sound silly in the beginning, but we will see what it means. If A is a set, then A is an object. In particular, I think I need ink. Give me a minute. Let me just quickly refill this. So in particular, given sets A and B, it is meaningful to ask whether A is an element of B. Okay, what does this axiom really mean? Suppose we have an object X and we have a set A. When we see the word object, as we are discussing something about sets, we have to understand that the use of the word object in this context is that any object has the potential for being an element of a set A. Okay, so that means I am allowed to ask the question whether X is an element of A or not. That is, whether X belongs to A is true or X does not belong to A is true. So what I mean by that is this: if I am given an object and any object whatsoever and any set A, then I am allowed to ask whether this is true or this is true. And the assumption is that exactly one of them has to be true. They of course cannot both be true. Also, it's not the case that neither of them is true or neither of them is false. Exactly one has to be true, and this is when we are given an object and a set. Now this axiom in particular assumes, it postulates that sets themselves are considered as objects, which means that if this X turns out to be a set after all, then I can consider it as an object. In particular, what that means is that if I am given two sets, say A and B, then it is meaningful to ask whether A is an element of B. That is, whether B is like this. It has A as an element and it has something else also. Or A may not be an element of B. Okay, so the assumption that sets themselves are objects is the first axiom. That's what this axiom means. Now, after this axiom, there is an informal example. So let's have a look at that. So this is my first rule of set theory, axiomatic set theory, that sets can be considered as objects. Now after that we have example 312. Okay, this example is also informal. Consider the set. You will realize why this example is informal. Now, axiom 3.1 we have understood, okay, so that is over. So this is something new. It will show another aspect of set theory. Consider the set which consists of two elements. I should not say two elements, or can I say write like this? After that I can write about this other set also. Consists of two elements 3 and 4 that are not sets and a set of two elements. Okay. What is the point of this example? In this example, we see that in axiomatic set theory that we are seeing right now, there are some objects which are not sets or not considered to be sets. Objects that are not considered to be sets. But of course, there are some other objects which are sets, right? So this is a set, as opposed to their natures are different. Now, this is an example of an impure set theory. An impure set theory is a theory in which not all objects are sets. In a pure set theory, every object is a set. That is, even numbers are modeled using sets, or numbers are defined using sets. So there comes the next remark. Remark 313. What this remark says is that there is something called pure set theory. In it, every object is a set or defined using sets. So every object is a set. For example, the natural number 0 can be identified with the empty set. Okay. The number 1 can be identified with this set, which is nothing but, okay, this equation may seems like it's wrong, but under this identification where I am identifying 0 with the empty set, this is meaningful. The number 2 can be identified with this set 0, 1, which according to the way we are identifying things, this turns out to be this set. Okay, so and so on. What have I written here? You see, when we developed the system of natural numbers, we said that our development is using piano axioms, but there we also mentioned that they can also be developed by some other means, specifically using cardinalities. Right? If you remember, we said that there are other ways of developing the system of natural numbers. The piano axioms are more, it's easier to develop in using the piano axioms. It's much more efficient to use the piano axioms to develop this system, because we can prove the properties, the basic properties, in a much easier way using the principle of induction, etc. However, cardinalities of finite sets can also be used to define natural numbers. So if we did that, then the system of natural numbers, that theory, okay, the system of natural numbers developed using the piano axioms or using cardinalities, they are going to give me identical results. But if I develop them using cardinalities, then my system becomes like some sort of pure set theory where numbers are also sets. Okay, so from a logical point of view, a pure set theory is easy because it has nothing but sets. We don't have different types of quantity or entities, like separately numbers, something else, sets, something else, functions, something else. No, everything ultimately comes down to sets. So from that point of view, a pure set theory is easier. But from a conceptual point of view, an impure set theory is easier to understand because we are already familiar with numbers in a slightly different way. You see how complicated this looks. Everything is set, that is fine, but this is 2, this is 1, and this is 0. So you can imagine that as you go to higher natural numbers, what the definition will look like. So because of that, impure set theory is easier to understand from a conceptual point of view. Now, whether our set theory that we are going to see here is pure or impure, that does not really matter, because the theory that ultimately comes out from an impure development or a pure development are more or less identical for the purposes of doing mathematics. So when it comes to the question of whether a given object, say 3 or say 2, whether 2 is defined using sets only or 2 is some other concept which has its own meaning, that question is not important to us. Okay, it does not matter whether we think of the number 2 as this set or 2 as this natural number by definition, or if you really go back to the piano axioms, this is true. It does not matter. So we are going to take an agnostic approach to whether a given object is a set or not. So this is just to let us know that such things exist, pure set theory, impure set theory, but it's not very important to us. As long as the sets that we get are having no contradictions, like the Russell's paradox, that is good enough for us for doing mathematics, and that's what we are striving for. Okay. Now, one more thing that I didn't address is why is this example informal? You see, so far we have seen only one axiom, right? Sets are objects. Now, as we go to higher and more and more axioms, the axioms will allow me to say this collection is a set, and again this collection, a much larger collection, is a set. So unless we get to those axioms, any example of set that cannot be justified using the given axioms, that is still, it does not exist for us. For us, this is still not a set. It will be a set when we introduce the axiom of pair sets, singleton sets, those things. Okay, so unless the existence of a set is justified by an axiom, it does not exist for us. So because we are using something which has no justification as yet, this is informal. Okay. Right, so the next thing, but before we go to any more axioms, now as we go on presenting the axioms, in the middle we are going to insert the concepts of set theory that we already know, like equality of sets, subsets, those things. Union will be an axiom itself, so that will come. But let us now look at equality of sets. So this is definition 314. Equality of sets. Which we already know, but still let us define it once more. Two sets A and B are said to be equal, which we write like this, written as A equal to B, if every element of A is also an element of B, and vice versa. That is, every element of B is also an element of A. Then we say that A and B are equal. Okay. Now here also there is something. The concept of equality, let's just have a short discussion on this itself. What is equality? Now we know that equality, from our prior knowledge of mathematics, we know that equality does not always mean two things being exactly identical, two things being the same thing. In mathematics, we come across several loose concepts of equality. Say, for example, in geometry, in ordinary two-dimensional Euclidean geometry, we have the notion of say congruent figures, but we also have a much more loose notion of similarity. Two triangles are similar if their corresponding angles are equal, or two triangles are similar if their corresponding sides are in the same ratio. So that is also one sort of equality. But the question is, if I have a class of objects of some time, of some same time. Say I have the class of all sets or the class of all natural numbers. A class of objects C of some time. And in this class I have the notion of equality. Say if I have two elements A and B in this class, then I say A is equal to B if something happens, some condition. That some condition determines what is the definition of equality. For example, here equality means that every element in A has to be in B and also the other way around. Now, you should not take this equality, the definition, so lightly. You see, if you are familiar with abstract algebra, you know that the definition of equality can come in various different types of fashion. Like, for example, if we look at the modulo group Z10, say the additive group of integers modulo 10. Here, equality has a definite definition. According to that, these two congruence classes, let me denote the congruence class of 12 modulo 10. Now, you will understand this only when you know this part of